Another thing that can limit productivity are nutrients. So, nutrients are all the various chemical things that phytoplankton need to do all the work they need to do. So, running all their little cellular machinery, keeping themselves alive, doing photosynthesis, all that stuff. Um, and the important concept here is a limiting nutrient. So that is the nutrient you don't have enough of. I think I talked about this in ecology as well. Basically, if you had more of that nutrient, you could make more phytoplankton. So, for example, one of the ways you can test what the limiting nutrient is just by like adding it to phytoplankton. So you got a bunch of phytoplankton and you add some nitrogen and then nothing happens. That means that probably wasn't your limiting nutrient. Whereas, like here in this case, they added iron, and when they add iron, suddenly there was a big increase in the phytoplankton, and so that seems like iron was probably the limiting nutrient. So we add a little more, so then you can have more phytoplankton. But importantly, phytoplankton don't need the same amount of all nutrients, just like you don't need the same amount of like protein and fat and carbohydrates and vitamins and minerals. Like you don't need the same amount of all that stuff. You need different amounts of all that different stuff. So it's the same with phytoplankton. They need different amounts, different nutrients. So we have something called the Redfield ratio. This is a ratio of these three kind of macronutrients that phytoplankton need to live and thrive and things like that. So it is 106 carbon to 16 nitrogen to 1 phosphorus. That's kind of the perfect ratio for phytoplankton to live with. So if one of those is at a lower amount than this ratio, that is probably going to be your limiting nutrient. Now, carbon is almost never limiting. So there's like usually plenty of carbon dioxide in the water. Sometimes you can run into carbon limitation if you're in an area, for example, where the water is extremely stagnant, like not moving. You can potentially run into some carbon limitation, but it very rarely happens. Because in most of the ocean, the limiting nutrient is nitrogen. So nitrogen is usually what phytoplankton don't have enough of. Although sometimes it's also iron. You'll actually be learning a little bit more about that in this week's assignment. So, how do nutrients get into the oceans? All these, we need all these important nutrients so that we can have productivity. There's a few different ways that nutrients get into the oceans. One we've already talked about, which is like upwelling, right? So when you get upwelled water, that water is usually pretty high in nutrients. Similarly, vertical mixing. So when you have this overturning of water, that can also help to mix these lower nutrients back up towards the surface. There's runoff, so just water running off the land and taking, dirt and sediments and other, nutrients with it, so they can come in through like rivers or even just through like rainwater running off the land and going into the ocean. You can also have decomposition. So we already talked about that a little bit, where organic matter is broken down back into nutrients so it can get recycled back into the food web. And lastly, dust. So dust can get blown across the ocean and it can carry nutrients with it. Again, your assignment for this week deals with that as a kind of catalyst for harmful algal blooms. Because of the interaction of light and nutrient limitation, you get these annual cycles in productivity, generally speaking. So you can see here, this is showing kind of time and then primary productivity. So this would be like January, this would be spring, this would be summer, this would be winter. My cats are running around. You tend to get the same pattern if you are in temperate areas. So temperate areas are the areas kind of in between the equator and the poles. So like we are in a temperate area here in California. So in the summer, for example, there's lots of sunlight, right? So light is definitely not limiting. You got plenty of sunlight, but you do have limited nutrients. And part of that is because there's not as much getting put in. Also, there's a pretty strong thermocline, right? Because you're heating up the surface of the water and then the lower water is cold. And so there's not much mixing. There's high level of stratification. So those deep nutrient rich waters are not getting mixed up back to the surface. So even though there's lots of sunlight, there's pretty limited nutrients. So you get some productivity, but not super high productivity in the summer. In the fall, there's some more wind. There's also a weakening thermocline. It's getting a little colder now at the top, so you no longer have that strong stratification. So that means there's a little more vertical mixing because of the wind and the weaker thermocline. So you get a little bit of nutrients coming up to the surface, and you still have a decent amount of sunlight. So you'll often get, I said bet, you get a small bloom in the fall. So a little bit of a peak in the fall. Now in the winter, you have storms and you have a lot of overturning as well. So lots of mixing, and you actually get a lot of nutrients getting churned up into the surface water. But now you have really low sunlight, so they're going to be sunlight light limited. So you'd still have pretty low productivity because of that low level of sunlight. And now, one of the things I mentioned was overturn. Overturn is when the surface water is cooling. So, like the air is colder than the water. So, the surface water is cooling and sinking, and then more is rising to the top. And so, again, you get this like kind of vertical mixing, overturning happening that, again, will bring the nutrient rich water up towards the top. So, again, you have high nutrients, but very low sunlight. So, still pretty low productivity. Now, springtime. Now we're cooking because you still have those high levels of nutrients left over from wintertime, but now you're getting more sunlight. So you have this mixture of like decently high sunlight and very high nutrients. Plus, a lot of time you'll have like a lot of rain in the spring, which will like wash even more nutrients into the water. And so you tend to get your largest phytoplankton bloom in the spring because you have, again, high nutrients left over from winter and from spring runoff, and you have a decent amount of sunlight. And again, it's not as high as the sunlight in the summer, but by the time it gets to summertime, even though we have high sunlight, at that point we've kind of used up all these nutrients, so there's not much nutrients left. So this is kind of showing a summary of that, where the green line is phytoplankton biomass. Again, you get this highest peak in the spring, and you get a little peak in the fall. And that's because this is showing the yellow is solar energy, so it's highest in the summer. But again, that's where nutrients are very low. This dotted black line is nutrients. So nutrients are very low in the summer, and so that's why you don't get much phytoplankton. But they're high in the winter, and so by the time we get to spring, we have pretty high sunlight and pretty high nutrients. So that's why we get that big spring bloom. And then in the fall, we get a little peak in nutrients because of that a little bit of overturning and mixing, and you still have a decent amount of sunlight, so you get that little peak in the fall as well. But then it's pretty low in the winter because even though nutrients are decently high, the sunlight is very low. Another thing we can look at is the zooplankton. This is kind of a preview for next week. So many zooplankton eat phytoplankton as a food source. So that means if you have more phytoplankton, there's also probably going to be more zooplankton, right? Because hey, more food for them. They're happy. But importantly, if we look at the phytoplankton here, so there we go. Phytoplankton is this green line again, and the blue line is zooplankton. So again, phytoplankton, zooplankton. And you'll notice peak in phytoplankton, peak in zooplankton, peak in phytoplankton, little peak in zooplankton. But there's a lag here, right? So first you get the peak in the phytoplankton, and then a little bit later you get the peak in zooplankton. That's because as soon as there's extra phytoplankton, the zooplankton can't just like clap their hands and make more, right? It takes a little time for the zooplankton to lay more eggs, and then for those eggs to hatch and grow up to adult zooplankton. So that is why there's a little bit of a lag in the zooplankton biomass after the phytoplankton. So, last question for today's lecture is, so far we are focusing on temperate latitudes. Do you think that these annual productivity cycles might be different near the equator or near the poles? So do you think it might be, do you think it might be different near the equator, and how do you think it might be different near the poles? So again, think about how the seasons work at the equator and the poles.